So now we'll turn to the second assumption, which is something we're more familiar with, which is the assumption of random sampling. So the sample that we are working with should be random, right? That means each observation in our sample should have an equal chance of appearing in the sample, right? So remember that we were saying that if we were to sample from a state, if we needed a sample of university students, right, we shouldn't stand outside the science building and then interview them about their GPA or their performance or their work experience and things like that. Okay, we should basically stand outside perhaps every building and collect this information so that each student has an equal chance of appearing in our sample. Okay, so that's the idea here. The third assumption is that we need sample variation in the explanatory variables, which is basically our x variable. So we need some sort of variation in x. Okay, basically saying that this outcomes on xi are not the same value, right? They shouldn't be constant. Okay, and this is the same as saying that the sample variance is not zero, right? If you basically have a graph where x doesn't change but y is changing, right? So x is not changing here but y keeps changing, then it's really not interesting to ask the question of what changes in x, how changes in x cause changes in y, right? This is not going to work out because there is no change in x. So it's not going to be an interesting question or not even a correct question to ask. Okay, so if all the x's are the same value, we are just unlucky and can't proceed. And typically this happens in very small samples. It can happen in very small samples, but hopefully we will not be working with that. And the last assumption here is this assumption of zero conditional mean, perhaps the most important assumption out of all, but all four are required. Okay, so we're basically saying that the expected value of u, which is our disturbance or our error, given x equals 0 for all values of x. Okay, so earlier we had said that the expected value of u is equal to 0, and we had said that the expected value of u given x1 should be equal to expected value of u given x2, and so on and so forth, right? So the expected value of u given any x should not vary, right? And so it should not vary with x, and this assumption is sort of this assumption can be violated. So here we can basically, even if we assume the expected value of u is some constant alpha naught, right? We had said that basically what happens is the intercept gets adjusted and the new error, the expected value of that is going to be 0. Okay, so we can compute the OLS estimates whether or not this assumption holds, but the problem is that if this assumption fails, right, if we don't have if this assumption doesn't hold, then your estimates beta naught and beta 1 hat are biased. Okay, so there's a theorem that says that we basically require all these assumptions that we said 1 through 4 for the unbiasedness of OLS. Okay, that basically, if you take the expected value of beta naught hat, that would equal beta naught, and if you take the expected value of beta 1 hat, that would equal beta 1, right? So this is basically if we were averaging our estimates over different random samples, that we would somehow get closer to that population parameter that measures the relationship between X and Y. Okay, so it's important to remember that unbiasedness is a property of the procedure or the rule of OLS. Okay, so let's take an example here. If we had estimated this regression of log wage on education, notice we have our intercept that was estimated and our slope coefficient. We could interpret this coefficient right here and say that 9.9% is an unbiased estimate of the return to education. We might want to say that, but that would be incorrect. Okay, technically, what we want to say is that this estimate that we've got, 9.9%, is basically an unbiased property of the OLS technique that we have used. Okay. So what we're saying is essentially that the rule used to get, the rule which is OLS, which is used to get beta naught hat and beta 1 hat, is unbiased, right? So our rule or our procedure is unbiased. So remember that. That's what we're saying. This is unbiased. Okay, so remember, these are the 4 assumptions we need to prove unbiasedness of our estimators. But here, this last assumption is crucial and usually will not hold in a simple linear regression model, right? There are going to be omitted factors, right? And we might want to ask the question, what are those omitted factors? And are they likely to be correlated with X? Okay, so if the correlation between U and X is not equal to 0, then we obviously have some omitted factors in our variables. And if that happens, then this last condition fails and our estimators are biased. We can also see this with another example, which is measuring student performance on math scores using student-teacher ratios in class. So if you think that student-teacher ratios matter for student performance somehow, then you can set up a model and you can estimate it. And this is using data that's available to you. So you can try this out. And there are 923 observations, and we have our R-square here. Okay, so this is basically saying that if this is a ratio, right, this ratio is going to range from 0 to 1. My apologies. So this is just a ratio for now. Just assume this is a ratio. And perhaps it cannot be less than 1, right? It would be hard for us to imagine a situation where so if this is the number of students and this is the number of teachers and this is equal to STR, that this is going to be less than 1, right? It's unlikely that you're going to have less than 1 student in a classroom. So at least 1 student per teacher, right? That's the idea here. Okay, so here we can see that our estimate of beta 1 hat is negative, right? And this is basically saying that 1 more student per teacher, okay, decreases the estimate pass rate on the math test by about 0.62 percentage points, right? And this is, this is intuitive. You can basically think that perhaps it is the case that if you have more students in a class, then the teacher cannot pay attention to students who need the teacher, and therefore there could be that negative association. But we have good reason to assume that the OLS estimator is actually unbiased in this is biased in this setting, right? Or we can question whether it is unbiased at all. So seems pretty likely that the OLS estimator would be biased. Okay, one reason could be that students from advantaged backgrounds would tend to go to schools with a smaller student teacher ratio, right? A smaller student teacher ratio is a good thing, right? This is good. And would likely, and those students who are coming from advantaged backgrounds, because they have a smaller student teacher ratio in their schools, they would perform better on average because maybe they are able to get more attention, right, on average. And this is all relative to, those without these small classes, right? So it could be the case that we're just picking up some sort of a negative correlation, right? Maybe if we look at the correlation between preparedness and class size, we can see that as class size increases, perhaps it is the case that there are less prepared students on average as class size goes up, right? This is just capturing that background, that advantage background that we were talking about, right? So this could be negative. It could be, it's possible, right? So there could be all these possible biases, and we will deal with those later. And we can also determine the size of these biases, a sign of the biases, and sometimes even the size, right? So that's the idea here. Okay, and we also noticed that the R square in this regression was really small, right? So notice this is like 1.4%. This is 1.4%. And so this is really saying that the variation that in Y is only 1.4% of the variation in Y is being captured by this student-teacher ratio, which is our X. Okay, so in other words, there are lots of unobservables in U, right? So we've left out a lot of factors that might be affecting those math scores. Now, the low R squared could also mean that this equation is going to be very poor for making any predictions about math scores. So if we were to solely just take data on, if we were to take these estimates that we got, beta naught hat and beta 1 hat, and if we were to use that equation to use some data on student-teacher ratios to predict, if we used all of these three things to predict math scores, this would be a very poor prediction. Okay. So we will take a look at what values might make sense and what values may not for this type of an example. So like we said before, STR, which is a ratio, number of students to teachers, cannot be less than 1. We will never really predict math 4 above the value of the intercept that we get, okay? So if you write out the equation, basically saying that STR cannot be less than 1, so at least math 4 is going to be 75.03, okay? And then we can also look into our sample. So if our sample is telling us that the smallest value is in fact further away from 1, it's the smallest value in the sample of STR, in the sample of this variable STR is 7.6, then the largest prediction for the math score, right, because they're negatively related, would be 70. Okay. But then again, if we look at our data carefully, then we would find there are over 300 schools that have pass rates in the math test higher than 70. Okay, so under prediction of these of all these schools is perhaps one reason why we're getting that R squared to be really low. Okay, so just to kind of recap here, we said that we need those 4 assumptions to prove that OLS estimators are unbiased. It's very likely that even if we are fine with the first 3 assumptions, right, that our fourth assumption gets violated. At least in a simple linear regression model, that is the case, okay? In the next video, we'll talk about the measure of dispersion or spread in the sampling distribution of these estimators, okay? And talk about what does that mean for our regression.